Good evening. Hello and welcome to the live interaction session of week 8 of this NPTEL course. So, we will start the live session now. I'm going to stop the video and uh, start the class. So again, I welcome you all to this NPTEL course. This course is the title of the course is Advanced Reinforced Concrete Design, and this course is brought to you by NPTEL. And the instructor of the course is Professor Surya Prakash from IIT Hyderabad. And presently, we are in week 8 of this uh, ongoing course. And this live session is brought to you by me. My name is S. Lalit Sagar. I am a doctoral candidate and PMR fellow in the Department of Civil Engineering at IIT Delhi. So, so today we are going to be solving some sample problems on the following topics. So, in the week 8 of this NPTEL course, we covered two modules. That is, in module 6, we looked into the analysis and design of reinforced concrete uh, members in shear, and in module 7, we looked into the analysis and design of reinforced concrete members under torsion. So, this is the distribution of the split of the module under three parts in module 6. So in module 6.1, we understood the underlying mechanism of reinforced concrete members under shear force. And in module 2, we understood the um, provisions of the Indian Standard Code, that is IS 456, when we are designing reinforced concrete members for shear. And in module 6.3, we looked into one of the design examples. And similarly, in module 7, we looked into the analysis and design of reinforced concrete members under torsion. And good evening to the participant who has joined right now. So I'm presently in slide number 2. So in module 7, we studied the analysis and design of reinforced concrete members under torsion. So it consisted of two parts. So in the first part, we studied the behavior of reinforced concrete members in tension. So how it affects the stress distribution and how to consider the torsion aspect in the design of reinforced concrete members. And in the second part, we studied the IS 456 provisions for reinforced concrete members under torsion. And we also looked at a few design examples for reinforced concrete members subjected to torsion. So, with that introduction, I think we can start today's sample problems. Uh, I hope that my screen is visible. Sir, is my screen visible to you? Okay, okay, thank you. So we can start today's session. Right. So today, again, it is going to be a combination of uh, conceptual or theoretical questions and numerical questions. And today we have prepared 18 questions because we are discussing two broad topics, that is One is the design for shear and other is the design for torsion. So today we are going to be solving approximately 18 questions. So without any further delay, let us start with the sample problems. So the first question is, which of the following statements are correct regarding the flexural and shear behavior of the beam? So there are uh, five statements or five options. So kindly have a look at them and let me know what is the correct response. So basically we are relating the design forces to the type of cracks that are being formed. I will wait for around 30 seconds, then we can proceed to discuss the correct answer. Okay. Now we can look at the correct answer now. So the correct answer is options C and D. C and D are the correct statements. So let us look at each of the questions now, each of the statements now. So the flexural cracks are usually normal to the longitudinal axis, and the shear cracks are diagonal in nature. So the words are interchanged. So the first statement is incorrect. And in the second statement, so compared to the flexural failure, shear failure is more brittle and more dangerous because the shear failure occurs without insufficient deformations and it can happen instantaneously compared to the flexural failure. So again, the words are interchanged, um, and the flexural failure is more ductile in nature, whereas the shear failure is more brittle in nature. So statement B is also incorrect. Now, statement C is correct because the reinforced concrete beams are designed in such a way that adequate shear reinforcement is provided because we want the beam to fail in flexure first. So if at all we want, if at all the beam fails, we want to induce the flexural failure so that it undergoes considerable deformation and it gives us sufficient warning prior to the failure. So option C or statement C is correct. And again, option D is also correct because reinforced concrete members are designed for bending moment first, and then depending on the area of steel that is provided, we'll be solving problems based on that later on. So depending on the area of steel that is being provided to resist the flexural forces, we are going to uh, design for the shear reinforcement. So statement D is also correct, and statement C is incorrect because we might have you might have already seen in this week's lecture that first we are going to design for bending moment, then we are going to design for shear. So they are sort of uh, independent of each other. So there is no conversion to equivalent bending moment as such. So for question one, the correct statements are statements C and D. Okay. So here is an example of a flyover where we can see that uh, here we can see uh, diagonal shear cracks being formed away from the center of the span, while at the central region of the span they are mostly flexural in nature. So the flexural cracks are perpendicular to the direction of the longitudinal axis. Okay. So with that, we can proceed to the next question. So again, this question is theoretical or conceptual in nature. In the reinforced concrete beam shown below, which type of cracks appear in region C under a uniformly distributed loading? So let us consider that the reinforced concrete beam is subjected to uniformly distributed load. What kind of cracks are observed in the region C? That is the question. So kindly
Flexural,
take a few.
hello,
Yes,
flexural.
yes. Hello. Yeah, please go ahead.
Sir, that C region is a flexural crack only, sir.
Okay. Thank you for the response. Uh, so, okay. So this image has been taken from the lecture slides. Has been taken from the lecture slide. Let us see what is the correct answer now. So, so the correct answer was option E. Now let us look at the answer why option E is correct. Okay. So this has been taken directly from the lecture slide, and here the region that I have indicated in this diagram, that is corresponding to the region C. It is a combination of flexural and flexural shear cracks. Okay. So I would like to just give a brief explanation of what is happening exactly in this region. So initially, when this reinforced concrete beam is subjected to a UDL, so initially there is flexural cracks appearing at the soffit of the beam. So soffit is uh, the bottom surface of the beam. So that is normal to the longitudinal axis. And then after a certain depth of the beam of the crack is penetrated into the beam, then it tends to form the flexural shear cracks. It tends to form the flexural shear cracks because of the principal tensile stresses. Okay, so here, uh, wait, let me denote that using the marker. So essentially, let me take a different color so that there is contrast. Okay, so basically, these vertical cracks that we can see, so those are the flexural cracks. On the other hand, the cracks which are initially formed as the flexural cracks, they tend to form a diagonal crack. Okay, this angle is around approximately 45 degree, and these are called as flexural shear cracks because they are initiated as a flexural crack, but they tend to crack at an angle because of the principal tensile stresses. Okay, principal tensile stresses. So these are the flexural shear cracks. Flexural shear cracks. So for that reason, uh, in the region C of the reinforced concrete beam, generally there's a combination of flexural cracks and flexural shear cracks. So the same thing is being depicted here in the lecture slides also. Okay, so for question 2, option E is the correct response. So with that, I think we can proceed to the next question. Okay, so we are going to solve some numerical examples now. So if we consider a if we consider a homogeneous beam having a width of 250 mm and overall depth of 500 mm, okay, and it is subjected to a shearing force of 400 kilonewton. Determine the average shear stress in the cross section. Okay. Kindly take a few minutes and let me know what is the correct response. I'm going to start solving the problem simultaneously. So for this rectangular cross section, the width is 250 mm and the overall depth is 500 mm. Okay. So in order to calculate the average shear stress, I have considered it as a homogeneous beam. You can consider it as fully uh, made up of concrete. It is fully made up of concrete. Now, how do we calculate the average shear stress? Average shear stress, that is tau V average is equal to Vu by B into B. So we can substitute the value. The shearing force is 400 kilonewton. Let us express all the forces in Newton and the dimensions in millimeter. Okay, this is 250. Excuse me. So which gives us a value of, okay, sir, I think for some reason your volume is less. Uh, okay. Can you please type the answer on the chat box because your voice is not very clear.
3.2 MPa is clear, sir.
Okay, okay. Yeah, yeah. Thank you. Thank you for the response. Yeah, indeed, it is 3.2 MP is the correct response, correct answer. Very basic problem. We'll proceed to the next question now. Okay. So in this question, we have determined the average shear stress. Okay. So irrespective of which location, um, excuse me. So irrespective of the location, we have determined the average shear stress. Okay, whether the point lies in the plane XX or YY, we have determined the average shear stress. And in the next problem, we are going to determine the shear stress at a particular point. Okay, let's say on this YY axis. So let us proceed to the next question. Yeah. So consider a homogeneous beam of width to 250 mm and overall depth 500 mm. The critical cross-section of the beam is subjected to a shear force of 400 kilonewton. Determine the shear stress at a depth of 150 mm from the top compression fiber. Okay. Kindly take a few minutes and let me know what is the correct response. I'm going to start solving the problem simultaneously with you. So what we are looking at here is a homogeneous rectangular beam, and the dimensions are same as the previous question. The only difference being we are going to determine the shear stress at a particular axis or a particular location. Okay, and here it is B is 250 mm and B is 500 mm. So we need to determine the shear stress at a depth of 150 mm from the top. Let us call this plane as XX maybe. So we need to determine the shear stress at this particular point. And this is 150 mm from the top fiber. So how do we determine this? Tau V is equal to V into Q divided by IB. So here what does each term represent? V is the shearing force, okay, and Q is the moment of the area about the axis considered. I is the moment of inertia of the cross section with respect to the neutral axis, and B is the width of the beam. Okay, so we'll start solving for each of these terms separately now. This one. Okay, so I think we can solve here. Okay, so as I said, tau B is equal to V into Q by I into B. Okay, and what is the shearing force? 400 kilometer. So V, let me mark the axis over here. This is the neutral axis. Neutral axis. So this is 150 mm, and the neutral axis is at a depth of 250 mm. Now V is equal to 400 kilonewton. Q is, we need to determine the moment of the area about the axis considered. Okay, so we need to consider the moment about this axis. So that gives us area into the centroid of this shaded region. That is, area is 250 by 150 into, we need to consider moment of this area about this axis. So we need to consider the centroid at which the center of gravity of this area lies, that is 150 by 2. Okay, so that will give us a value of 2812.5 into 10 to the power 3 mm cube. That is Q. Now I is given by BD cube by 12 for a rectangular cross section, right? That is 250 by 500 cube divided by 12, which gives me a value of 2604.167. 2604.167 to 10 to the power 6 millimeter power 4. And B, as we know, is 250 mm. So when we substitute all these values into the shear stress equation tau v, let us say it is at x axis. Tau v x is equal to into 6 into 250, which gives me a value of 1.728 MPa. Okay. Sir, can you please check and see if you're getting the same answer?
Yes, sir. It
Okay,
is
okay,
1.73 mk.
okay. Thank you. Okay. So the correct response is option C is the correct answer. Okay. So this is how we calculate the shear stress at a particular point. As I explained earlier, first we have determined the average shear stress. Then we are going to determine the shear stress corresponding to a particular axis or a particular point. Okay. Let us proceed to the next question. So for the homogeneous beam, that is the same beam that we considered in the previous question, subjected to the same shear force, determine the shear stress at mid depth of the cross section. Okay. Kindly take a few seconds and let me know what is the correct answer. Is the neutral axis. So there are two ways of solving this problem. Uh, that is, first is the using the equation that we already discussed, and second is the shortcut which I'm going to explain you after solving the first part. Okay. So here tau v neutral axis is equal to v into q divided by I into b. So the thing is, we can use a lot of data that we calculated from the previous problem, but the only change is going to be in the term q. Okay, so q is equal to a into y bar. Okay, that would be 250 by 250, that is 250 by 250 multiplied by the centroidal height. Okay, from the neutral axis, the centroid of this area is at a distance of 250 by 2, that is 125 millimeter. Okay, which gives us a value of 7812.5 millimeter cube. This is the q value. Now let us substitute the values and find out the value of the shear stress at the neutral axis. V is 400 into 10 to the power 3. Q is okay, I think this has to be into 10 to the power 3. Sorry for that. 7812.5 into 10 to the power 3 millimeter cube. 7812.5 into 10 to the power 3 millimeter cube divided by I is same because we are calculating the moment of inertia above the centroidal axis or the mid height, that is 2604.167 into 10 to the power 6, and B is as usual 250 millimeter, which gives us a value of 4.8 MPa. So kindly verify this answer. So this is the first method, that is using the equation to determine the shear stress. But whenever there is a question which asks you to determine the shear stress at the neutral axis, there is a shortcut. So that shortcut is that tau V max is equal to 3 by 2 into tau V average. Okay, so if we consider the shear stress distribution across the depth of the cross section, right? I'll take a different thing. So it usually forms a parabolic profile. Okay, sorry for that bad diagram. Okay, so this is it forms a parabolic profile, and we can represent the average stress using this dotted line. Okay, so let us call this point as tau V max, and this rectangular dashed box is tau V average. So let us say that if we are able to calculate the tau V average for the cross section, we can obtain the maximum shear stress, that is at the centroidal axis, by multiplying it by a factor of 1.5. Okay, it's as simple as that. So we already found out the tau V average. So tau V max, or tau V neutral axis, is equal to 1.5 into 3.2, which gives us the exact same answer, that is 4.8 MPa. Okay, but please keep in mind that this is applicable only for determining the shear stress at the centroidal axis. Okay, so if the axis under consideration is having a slight offset also, this uh, particular equation does not hold good. So the correct answer is option E. Okay, so I hope that you are able to arrive at the correct answer. With that, we can proceed to the next question. Okay. So we have a conceptual question. Okay, which of the following factors does not contribute to the development of internal resistance or shear stress in a beam with transverse reinforcement? Okay, kindly look at the options and let me know which of these factor does not contribute to the shear resistance of a cross section with the stirrups. So out of these five options, actually four of the factors contribute to the shear resistance, but one factor does not contribute. Okay, I think we can have a look at the answer now. So it was a slightly trickier question, which I developed from the lecture slides. So the correct answer is Option D. Option D, that is shear in the cracked concrete, is not considered to determine the shear resistance. Okay. Let us look at the answer why. So as we can see here in this equation, the resistance from the concrete is considered to be a sum of various factors. Okay. So here is the shear resistance coming from the concrete. So VCZ is the shear resistance by the uncracked concrete. Okay. And then VA is the shear resistance caused by the interlocking of the aggregate particles. Okay, that is VA. And VD is the double action uh, due to the longitudinal reinforcement. That is VD. Okay. And then we have the resistance provided by the stirrups or the transverse reinforcement. Okay. So nowhere in this uh, shear resistance mechanism do we have the role of the shear resistance provided by the cracked concrete. Okay. So only the shear resistance from the uncracked concrete is considered, but the resistance by the cracked concrete is neglected. Okay. So here, as we can see, so initially we are going to consider the resistance as a sum of the resistance by the uncracked concrete, then the interlocking of the aggregate in the concrete, then the double action due to the longitudinal reinforcement, and ultimately the resistance from the transverse reinforcement or the shear reinforcement or the shear stirrups. Okay, so option D is the incorrect statement and the right answer for this particular question. So we'll proceed to the next question now. So as per IS 456-2000, the design shear strength of concrete, that is tau c, of a reinforced concrete beam depends on which of the following factors. Okay, kindly have a look at this statement carefully and let me know what is the correct response. So which of the following factors are considered to determine the value of tau c, that is shear strength of the concrete? So to give you a hint, there are two correct factors out of the five options given.
C one correct answer, sir.
Okay, okay. Thank you for the response. So I'm going to give you another hint to help you. So just to provide you a context, sir, I hope that my screen is visible. You're able to see the table.
Yes, sir. Visible, visible.
Okay, okay. Thank you. So we are basically looking at this IS 456 table 19, which is on page number 73 of IS 456, and we are going to determine the design shear strength of concrete, that is tau c, using this table. And basically, there are two factors which are considered in order to determine the value of tau c. So one is the grade of concrete, other is the area of the tensile reinforcement. Okay, so here we can see in the note, the term AS represents the area of longitudinal tension reinforcement, and here we have the grade of concrete. So depending on the grade of concrete, the design shear strength will also vary. Okay, so in this particular question, I was looking at two factors which actually contribute to the design shear strength. That is options A and C. Okay, so first we have the grade of concrete. So as I showed earlier, depending on the grade of concrete, as the grade of concrete increases, the design shear strength increases. And secondly, the percentage longitudinal reinforcement in tension, because here AS corresponds to the longitudinal tension reinforcement So it does not really depend on the compression reinforcement, mainly using these two factors, that is the area of tension reinforcement and the grade of concrete. We are going to determine the design shear strength. Okay, so for this particular question, options A and C are the correct responses. So moving on. Yes. So again, we have a conceptual question. As per IS 456 2000, what is the influence of axial forces on the design shear strength of concrete? So the question is, whenever there is axial force, uh, or the axial compression or axial tension, how it influences the design shear strength. Okay, please take a few minutes and let me know what is the correct response. I think we can have a look at the answer now.
A and C, sir.
Okay, okay. Thank you for the response. But I think there is only one correct answer for this question. So if you would like to try again, I'll be happy to wait. There is only one correct option. So the correct answer is option B. Okay. The shear strength increases with increase in the actual compression. Okay. So again, it has been adopted from the lecture slide. That is as per clause 40.22 of IS 456. Here we can see the screenshot of that provision as well. So the design shear strength shall be multiplied by a particular factor which is determined using this equation, that is delta is equal to 1 plus 3 pu by agfck. So this pu has to be actual compression. Okay, so whenever there is a compressive force, there is an increase in the shear resistance of concrete. Whenever there is a compression force, there is increased shear resistance. But whenever there is a tension, axial tension, the shear strength may actually decrease. Okay. So the correct answer is option B. Okay. So with that, I think we can proceed to the next question. Yeah. So if an interior beam column joint, uh, the beam has to be designed for shear. If the beam is subjected to a load of 500 kilonewton at 50 centimeter from the column face, where is the critical section for the shear located? Okay, I'm going to draw a small diagram over here to facilitate better understanding. So we have an interior beam column joint. So we have this interior beam column joint, and we are considering that the depth of the beam is 40 centimeter, okay, or 400 mm. That is the, yeah, effectivity. Now the question is that we are there is a concentrated load acting at 50 centimeter from the column face, 500 kilonewton, acting at a distance of from the column face. So which would be the correct location of the critical section for the shear? So the question is, so whether you're going to consider the critical shear at the face of the column or at a distance of d from the column face. Okay, let me call it as xx. Xx is the face of the column, and we have another section at a distance of d from the column face. Let us call it as yy at a distance of 400 millimeter or any other cross section. Okay, so the correct answer for this particular question is option E. We need to consider at the face of the column. And here, again, this question has been adopted from the lecture slides. And here are the corresponding IS code provisions also. So the thing is, if there is a heavy load acting within uh, a distance of 2D from the face of the column, then this dashed line that corresponds to the critical section. Okay, but if there is a uniformly distributed load acting on the beam, then we may safely consider the critical section at a distance of d from the column face. Okay, so here we can see the corresponding provisions, clause 26.62 of IS 456 and clause 40.53 of IS 456, which has the details on how to consider the critical cross section depending on the type of loading acting on the beam. Okay, so I request you to please have a look at it later on. So the answer is whenever there is a heavy load acting within a distance of 2D from the face of the column, then the critical section has to be considered at the face of the column. And here D corresponds to the effective depth of the beam. Okay, D is effective depth of the beam. So for this particular question, option E is the correct response. Okay. So moving forward, so we are having a numerical problem now. We are going to design the reinforced concrete beam for shear. So the data is as follows. So for a rectangular reinforced concrete beam, which is having a size of 300 by 600 mm, and the span is 4 meters, and it supports factored load of 60 ton at its mid span. Okay, and the reinforcement details is as follows. That is 4 bars of 25 mm diameter of Fe 500 grade steel. Determine the design shear force for the beam. Okay, so I will draw a sketch over here so that we can solve it together. Right. So let us consider this as the support. To a load of 60 ton. So 60 ton is 600 kilonewton basically. 60, 1 ton is 1000 kg, 1000, and in order to, oh sorry, it's 100 kg. Then we need to convert it from Newton to kilonewton, right? So that turns out to be 600 kilonewton. think there was a small confusion in the conversion actually. So 1 ton is 100 kg. Okay, 100 kg. So these many kgs divided by 10. This gives the 3. Okay. Okay. So what would be the design shear force? It's quite straightforward. So 600 divided by 2, 300 kilonewton. Okay. So again, it's a very straightforward problem. So the design shear force for the beam is 300 kilonewton. Option A is the correct response. Moving on. Now, for the beam given in question 10, determine the spacing of transverse reinforcement or stirrups considering two-legged 10 diameter stirrups of grade Fe415. Okay. And take M30 concrete. Okay. So I'm going to be solving the problem along with you now. Okay. So we have 300 by 600 So the width is 300 millimeter. Just focus. And the depth is 600. And then we are going to consider a effective cover of 50 right? 50 and then the effective depth would be 550 millimeter. Okay, and then we have Vu is equal to 300 kilonewton. So whenever we are designing the shear stirrups, right? So this Vu has to be VUC VUC. Sorry for that. VU is equal to VUC plus VUS. So VUC is the contribution from concrete, and S is the contribution from the shear reinforcement or the stirrups. Okay. So how do you find out VUC? VUC is equal to tau C into BD. So tau C, as I already shown earlier, it comes from table 19 of IS 456. And to get the value of tau C, what do we need? We need the grade of concrete and the percentage of tensile reinforcement. Okay. So we know that the grade of concrete is M30, right? So we have M30 and we need to determine the value of PT. So PT is given by 100 into AST by BD. So what is the value of AST? Let us calculate. AST is 4 of 25 that.
192.5 square.
Yeah, thank you. Thank you so much. 4 of 25 diameter, that is 1963.5 square. So what would be the PT value now? PT is equal to 100 into AST by BD. That is 100 into 1963.5 divided by BD. B is 300, and please note that we are taking the effective depth, that is 550. So what is the value of PT we get? PT value is One,
1.19.
yeah, thank you. So the PT is 1.19%. Now let us go to table 19 and see what is the corresponding tau c we are going to get. Okay, so let us go to table 19 for M30 concrete. Corresponding to 1% we have 0.66, and corresponding to 1.25 we have 0.71, 0.66 and 0.71. This is PT tau c. So for 1% and 1.25%. Okay. So after doing the interpolation, I got the value of TC as 0.698 MPa. Okay, let us go to the next slide and continue the rest of the problem. So, yeah, that is, there are two ways of determining the value of TC, that is tau c. So tau c one can be from this particular equation, or we can take from table 19 of IS 456. So we got the value of tau c as 0.698 MPa. I hope that my handwriting is visible. If it is not, please let me know. I will try to improve. Um,
Okay, sir, it's visible.
okay, okay. Thank you. So we have VU is equal to VUC plus VUS. So now we need to design the stirrups. Okay, so VUS is equal to VU minus VUC. Okay, that is 300 into 10 to the power 3 minus, what is VUC? VUC is equal to tau c into B into D. That is 0.698 into 300 into 550, which gives us a value of, I'm getting,
115.17 kilometers.
okay. Thank you. I'm just going to check that. Yes, it's 115.17 kilonewton. 115.17 kilonewton. Now, yeah, so VUS is equal to 300 minus that answer, 184.8 kilonewton. 184.83 kilonewton. Now we need to determine the spacing of the stirrups, and for the spacing I'll take a different color now. Vs is equal to 0.87 Fy ASV into D divided by SV. So before determining the value of SV, we need to determine the value of ASV. So it is given that we have to consider two-legged 10 mm stirrups. Okay. So ASV pi by 4 of 10 square multiplied by 2 which gives us a value of 100.53 mm square. And as per the IS code provision, it is given that Fy has to be maximum of 415, or it should not be greater than 415 MPa. So let us substitute all the values and see what we are going to get. So we can write SV is equal to 0.87 into 415 into 100.53 into D is 550 divided by 184.83 into 10 to the power 3. Can you please calculate and tell me what is the SV we are getting?
108 mm.
Okay, can you please verify? Because I'm getting value of 169 mm. I will also cross check that once again. Because here Fy has to be 415. Okay, we cannot. Oh, okay, it is 108 actually. Okay, I think I had considered it as 12 mm diameter. So for 12 mm we are going to get this value. But for this 10 mm it has to be 108 mm. Okay, so please make this correction. So consider it as a 12 mm stirrups. For 12 mm, please check if you're getting the same answer. For 12 mm, ASV is equal to pi by 4 into 12 square into 2, that is 157. Oh, I'm sorry, I'm sorry. I think I made a mistake over here. I'm very sorry.
12 mm 242 coming.
Yeah. Sorry, I got confused actually. So, so basically this particular number is wrong. So this has to be, okay, so this is incorrect because this corresponds to 8 mm dia stirrups, but for 10 mm, ASV will be 157, 157.08. Okay, so when we substitute that value, sir, please check now if you're getting the same answer. So please verify this number first, and then you can verify this one. Okay, so I'm getting ASV as 157, and let us substitute that value here and find out the spacing. 7, 2, I'm getting a value of 169 mm. So the correct answer is option D. Yeah. So I hope you were able to get the answer now.
Okay, sir.
Okay, okay. No, please, if there is any doubt, let me know.
Yeah, sure, sure.
Yeah, yeah. I hope you got the correct answer. 169 mm. We can wait, actually. We can pause for a minute or two so that you're able to get the answer.
Yes, sir, we got it. With 157.06 means we got 169.
Yeah, yeah, exactly. Yeah, sorry for that confusion, actually, because I'm habituated to the 8 mm stirrups. So that's why I wrote this number. But when we're using two-legged 10 mm stirrups, this is the corresponding value of ASV. And as you might be knowing, like whoever has done, a course on reinforced concrete design, we can vary between 8 mm, 10 mm, and 12 mm so that we get the desired spacing value. So when we are sending the drawings to the site, so we try to keep this ASV between 150 to 200 mm in order to prevent the congestion of the reinforcing steel. So we tend to uh, you know change uh, play with these diameter values. So if we consider 10 mm diameter stirrups, then we get the value of spacing as 169 mm, and approximately on site we can go for 150 mm or 6 inches. Okay, so we'll proceed to
Okay.
the next. Yeah,
Okay.
we'll proceed to the next question now. So in the previous question, we solved a beam which is subjected to concentrated load. Now we will take up a beam that is subjected to the UDL. Okay, so for this beam configuration, the question is determine the design shear force. Okay, please take a few seconds and let me know what is the correct answer. So we have um, the, the beam here, and the center to center distance
270
is
kilometers easy.
okay. So there is a slight catch over here. So because it is subjected to UDL, the critical section will be at a distance of D from the support. Okay. So the answer requires a slight modification. So this will be the critical section at a distance of D. So D here is 550 mm. Okay. Please, you can calculate using that. Now, so it is subjected to a UDL. So this is 90 kilonewton per meter. So the reaction is, as you said, so let us call it as R. R is equal to 90 into 6 divided by 2, that is 270 kilonewton but the critical section lies at a distance of d from this central plane. Okay, so the design shear force would be 270 minus 90 into 0.55. So with that information, please let me know what is the correct answer.
220.5.
Yeah, thank you. So thank you for the response. So if we consider this, if we consider this XX plane as the critical section, which is at a distance d from the central point. Okay. So the correct answer is 220.5 kilometer. So now we'll go ahead and design the beam that is subjected to UDL. So for the beam given in question 12, determine the spacing of transverse reinforcement considering two-legged 8 mm stirrups. Okay. So we'll solve the problem together simultaneously. So we know that VU is equal to VUC plus VUS, where VUC is the contribution from concrete and VUS is the contribution from the shear reinforcement. Okay, I think there's a cross section. The cross section is not given. And what is the area of reinforcing steel? 4 bars of 25 mm diameter. That is say AST is 5 by 4 of 25 square into 4, that is 1963.5 mm square. And um, FCK is 30 MPa and FY. So FY is 500 for the longitudinal reinforcement, and for the shear stirrups it is FYS is 415 MPa. So again, the thing is, in order to determine this VUS, we need the value of, sorry, VUC, we need the value of FCK and PT. Okay. So PT is the same as, the previous one, that is 1.19%, and correspondingly, tau C is 0.698 MPa, because the data is same from the previous problem, right? So let us go ahead and calculate the value of VUS. Is VUC tau C into VD, 0.698 into 300 into 550. So VUC is SVC 115.17. Okay. So VUS is, what is VU? 220.5. VUS is, yeah,
105.3.
yeah, thank you. 105.8. 0.3, right? 105.3, right?
Yes, sir.
Yeah, okay, thank you. So VUS is 105.3, and we know that VUS is 0.87 Fy into ASV into D divided by SV. So ASV over here is 100.53. Okay. Again, sorry for that mistake in the previous question. So when we
No, no
consider,
problem. No
yeah,
problem.
when we consider 8 bars, that is pi by 4 into 8 square into 2, we get the value of 100.53, right? So let us find out the value of SV. SV is 0.87 into 415 into 100.53 into 550 divided by VUS, that is 105.3 into 10 to the power 3. I'm getting a value of 189 points.
108.4.
Yeah, 189.6 mm. Okay, so this is the spacing that needs to be provided. Okay, so yeah, so option B is the closest response, right? So we can say that provide two-legged 8 tall stirrups at, let us say, 175 mm center to center. But after calculating this spacing, there are other, certain provisions as per IS 456 that we need to check with, right? So it would be incorrect, without. So we need to check these provisions before providing the actual reinforcement, right? So one is that we need to provide a minimum spacing of 300 millimeter, or we need to provide a minimum spacing of 0.75D, which turns out to be 412.5 mm, or it has to be 0.87 Fy into ASV divided by 0.4B. Okay, so let us substitute that and see what is the value we get. Let's calculate that value. Be 02.5. So as per the IS code provisions, we have these values: 300 millimeter, 0.75D or 0.87 FY ASV divided by 0.4B, which turns out to be 302.5 millimeter. And we have from the design this 189.6. So out of these four values, we need to provide the least of these four values. Okay. So on that basis, we can say that option B is the correct response. Okay. So with that, I think we can proceed to the next question now, because we have another five questions for today. So we have another five uh, design problems for today, and we're going to be looking at some problems on designing for torsion as well. Okay,
Okay. Uh,
okay. So with that, we'll proceed to the next question. Yes. So again, as I was telling, so we are going to be considering two big problems for torsion. So one is subjected to pure torsion, and other is going to be subjected to torsion, moment, and shear. Okay. So please take a few minutes and read this problem. Then we can solve the problem together. Okay. So we have a rectangular reinforced concrete beam. I'm going to sketch the cross section. 600 overall depth, right? We need to determine the area of the reinforcing steel. So take FCK as 30 MPa and Fy as 500 MPa. Please note that this Fy is for the longitudinal steel. Okay. And it is subjected to a factor torque of 75 kilonewton meter. That is, Tu is equal to 75 kilonewton meter. So what happens is, whenever a beam is subjected to a torque, we are going to determine the equivalent moment and the equivalent shear. So that is the philosophy, the design philosophy. Whenever we encounter a reinforced concrete beam subjected to torque, we are going to convert it into an equivalent bending moment and equivalent shear force, and then we are going to proceed to design the RC beam conventionally. Okay, that is the design philosophy. So now let us further look at the problem. Yes, so this is what I was talking about. So whenever we have a torque or a torsional force, we are going to convert it into equivalent bending moment and equivalent shear. Then we are going to proceed with the design conventional. Okay. So here we have the moment due to torsion, that is mt, is equal to tu into 1 plus b by b divided by 1.7. Let us substitute that value. This is 75 10 to the power 6 to 1 plus what is the overall depth? 600 by 300 divided by 1.7. So I get the equivalent moment as, please verify if you're getting this answer. Okay. So here it has to be ME. So we are going to be solving it later on. ME1 and ME2 is equal to MT plus or minus MT plus or minus M. This is the equation, right? So we need to design this beam for a moment of mu is plus or minus 132.35 kilonewton meter. That is, we need to design it for the positive moment as well as the negative moment, or sagging, which is the positive moment, or hogging, which is the negative moment. And this mu becomes 0. Okay. So now let us proceed to design this. So we have R is equal to mu by bd square. That is B is 300. So I'm getting a value of 1.458. Okay, so once we get the value of R is equal to 1.458, I'm going to write it here. We can use many different ways of determining the area of reinforcing steel. Okay, so I'm going to solve it using the direct calculation method, which we looked at in the previous class. So R is equal to 0.87 Fy into Pt by 100 into 1 minus Fy by Fck into Pt by 100. Or we have Pt by 100 is equal to Fck by 2Fy into 1 minus square root of 1 minus 4.6 R by Fck. Right. So we'll try to solve the problem over here. So Pt by 100 is equal to Fck is 30, right? So from this, I got a value of Pt is equal to 0.356. So Pt is equal to 100 into AST by BD. So AST is equal to PT into BD divided by 100. Okay. Correspondingly, I am getting a value of 588.3 mm square. Okay. Please check that if you're getting this, whether you're getting this answer. 0.356 into 300 by 550 divided by 100. Okay, so we should be able to get the answer of 588.3 mm square. Sir, I hope that you're able to get this answer.
Okay, so I will try. I will try.
Yeah, 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 please. Or actually, there is alternative way also. There is a shortcut method using SP16 that we can discuss later on. Okay, but first we'll make sure that we are getting this answer. 1 minus 4.6 into 58 divided by 30. The root of the same. 1. Okay, so we will get the value of PT when we substitute these values. 30 by 2 into 500 into 1 minus square root of 1 minus 4.6 into 1.458 divided by 30. Upon simplifying, we get the value of PT as 0.356. So PT is 100 into AST by BD. So AST is PT into BD by 100. So we can get the value of AST as 588.3 mm square. Okay, so there is an alternative way also of finding the PT value. So that is using SP16, right? So we can have a look at this page 50. Please make a note, page 50 of SP16. So you can find out the value of mu by bd square. Okay, so we have mu by bd square as 1.458, right? So 1.458, then corresponding to Fy of 500, right? We will get a value between 0.355 and 0.368. Okay, from interpolation you can find out the value of PT as 0.356. Okay, so this is a very effective way of finding the value of PT. That is page number 50 of SP16. Using these tables, we can obtain the value of PT.
Okay, sir.
Okay, okay.
Understood.
Yeah, yeah. So there are two ways. One is using the equation or using the page number 50 of SP16. We can arrive at the value of PT. And the corresponding AST is 588.3 mm square. So option C is the correct answer. Okay. And let us provide a 3 bars of 16 diameter. Okay, AST provided is 3 bars of 16 diameter. Yes, pi by 4 of 16 square into 3, which gives us an answer of 603.2 m square. 603.2. We are going to be using this in our next question. Okay. So for this question, we need to determine the shear reinforcement. Okay. We can start solving the problem simultaneously. Again, uh, again we are doing it for, we have already done for several lines over here. I'm going to reiterate the procedure once again. Okay, so V is equal to VU is equal to VUC plus VUS. Okay, now VUC we can find out using the value of PT and FCK, right? So we know that FCK is 30 MPa and PT is 100 into AST by BD, that is 100 into 603.2, right, divided by BD. BD is 300 divided by 550, right? So we get the value of PT as how much?
0.35, 0.36.
Okay. Okay. Thank you for the response. Yeah. PT is 0.36. 3656. And I forgot to, mention a very important aspect. So how do we convert this torque to the shear? That is using this equation, right? VE is equal to VU plus 1.6 TU into B. Okay. VE, I'll take a different color. VE is VU plus 1.6 TU by B. That is 1.6 into 75 into 10 to the power 6 divided by B, that is 300. So what is the value of VE that we are going to get? 1.6 into 75 into e to the power 10 to the power 6 divided by 300, which is 400 kilonewton. So for this particular question, when a torque of 75 kilonewton meter is applied, the corresponding design shear force is 400 kilonewton. Okay, please note that. Now let us go back to calculate the value of VUC. VUC is equal to tau C into BD. Now corresponding to 30 MPa and PT of 0.3656. 0.3656. Let us look at IS 456. Yeah, so it has to lie between this value of 0.37 and 0.50. So I'm getting a value of tau C as 0.43 MPa. Okay, please verify that later on. Okay, so VUC is equal to 0.43 into B is 300 and D is 550. So the corresponding resistance by concrete is 70.95 kilonewton. 70.95 kilonewton. So VUS is equal to VU minus VUC, that is 400 minus 70.95 is equal to 329.05 kilonewton. Right now, again, we go back to the usual calculation. VUS is equal to 0.87 Fy into ASV into D by SV. So it is given that we need to design using two-legged 12 mm stirrups. Okay, let's be extra careful while calculating the ASV now. Pi by 4 into 12 square multiplied by 2, that is,
226.06.
yes, yeah, thank you for the response. 226.19 I'm getting. Okay, so we have SV is equal to 0.87 into Fy is, let us consider 415, right? Yeah, 415, and 226.19 into D is 550 divided by VUS. Okay, so the reason why we are taking this 12 mm diameter is the shear to be resisted by the stirrups is very high. So this 330 kilonewton is very high, which is why we are going for a high diameter stirrup, that is 329.05 into 10 to the power 3. So we get the spacing as, I'm getting the spacing as 136.5 millimeter. Okay. So option D is the correct response. Okay, please verify that you're getting this answer.
Okay.
Okay. So we have, yes, we have another three questions, I think, for today. Yeah, so let us, without any further delay, I'll be taking maybe 5 minutes extra, but we'll try to get through these three problems now.
Okay, no problem.
Okay. Thank you. Uh, so the question is, we have a rectangular reinforced concrete beam of size 300 by 600 mm. It's having a span of 6 meter, subjected to a sagging moment, that is positive moment of 120 kilonewton meter, and the shear force is 60 kilonewton and torque is 80 kilonewton meter. Determine the equivalent bending moment and the shear force due to torsion. So, as we discussed earlier, in the previous problem, we subjected the beam to pure torsion, then we converted it to the equivalent moment, equivalent shear force, then we perform the design. So, in this case, we have this design moment is there, design shear force is there, and then a torque is also there. From this, we are going to reduce it to equivalent bending moment and equivalent shear force, and then we are going to design the reinforced concrete beam. Okay, we can start solving the problem simultaneously. Okay, we have the, okay, so we can use this equation over here. I'm going to copy these two to this slide and we can start solving the problem. Okay, this will help us in solving the problem, right? So in the first part, we need to determine the equivalent moment, that is MP is equal to PU into 1 plus B by B by 1.7. Okay, what is the torque? Torque is 80 kilonewton meter. Okay, 80 into 10 to the power 6 into 1 plus what is D? 600 by 300. 600 by 300 by 1.7. So that will give us the equivalent bending moment. And how do we find out the equivalent shear force? Okay, equivalent is equal to, let us ignore this term. Okay, so we are only looking at the equivalent shear force due to the torque. That is what 1.6 into Tu by B. So please tell me what is the value we get when we simplify this equation.
Mu 141.76
Yes,
and
yes,
V equivalent 426.66.
yes, yes. Okay, thank you very much for the response. Now it is 141.2, 426. Yes, so option A is matching correctly, so the answer is absolutely right. Okay, now we'll proceed to the next part of the question. Now we need to design the beam for flexure, that is, we need to determine the tension reinforcement and the compression reinforcement. Okay, now let us proceed to solve the problem. We know that ME is MU plus or minus MT. Okay, MEQ1 and MEQ2 is equal to MU plus or minus MT. So that is MU is how much? 120 plus or minus 141.2. So MEQ1 and MEQ2 would be much 261.2 kilonewton meter and minus 21.2 kilonewton meter. Okay, these are the equivalent moments for which we need to carry out the design. Similarly, okay, we look at um, the shear problem later on. Okay, let us design it for the bending moment now. Okay. Now, before proceeding to, we need to make a choice whether to design it as a singly reinforced beam or a doubly reinforced beam. Okay, and we have this value of mu limit is equal to 0.138 BD square. Okay, so this is coming from, yeah, so if we go to the table C of SP16, we have the limiting value of the moment of resistance. For FE415, we have mu limit by FCK BD square is 0.138. Okay, so if I remember, I think last class we had this problem. So depending on the grade of steel, we can use these coefficients accordingly.
Yes, yes.
Yeah, yeah. Okay. So it is in SP16, and I think I'll give you the page number also. It is page 33. Wait, let me see. Yeah, I think page number 10 of SP16. So corresponding to different grades of steel, we can get different values of mu limit by FCKBD square. Okay. Okay. So let us calculate what is the value of mu limit. 0.138 into 30 into 300 by 550 square. So we get the value of mu limit as 376 kilonewton meter.
375, 375.
Yeah, yeah. So we can very much design it as a singly reinforced beam engine. Okay. So now let us proceed to design the beam. 261.2. Okay. Now again there are two options to design this problem. To design the beam. So let me pull up this equation. We are using this direct method, or we can use the shortcut method also using SP16. Right. Yeah. So we have PT by 100 is equal to FCK by 2FY into 1 minus square root of 1 minus 4.6 R divided by FCK. So what is the value of R? To take a different color just for better contrast. R is equal to mu by um, BD square. That is 160, sorry, 261.2 into 10 to the power 6 divided by 300 into 550 square. So R is equal to 2.878. So while we are at it, we'll try to find out the value for mu is equal to, remember that we need to design for 21.2 kilonewton meter also. So correspondingly, R will be mu by BD square, that will be 0.233. Okay. Now let us proceed to find out the value of PT. PT by 100 is equal to FCK is 30 if I'm not mistaken. Yeah, 415, right? 30 divided by 2 into 415 into 1 minus square root of 1 minus 4.6 into 2.787 divided by 30. So this gives me value of PT as 0.9128, right? Please check that you're getting this value. PT is equal to 100 into AST by BD, right? So AST is equal to 0.9128 into 300 into 550 divided by 100. Okay, so simplifying this, I'm getting the value of AST as 1506 mm square. Okay, so option C, we got this value. Now let us see for the compression reinforcement. Okay, so for the compression reinforcement, I'm getting a very low value. Okay, that is corresponding to this value. I'm getting AST as 107 mm square, but this is very low value as per clause 26 point. We have the, okay, I'm going to take another color. Okay, as per clause 26.511, okay, the minimum has to be 0.85 BD divided by Fy. Okay, you may please check later on. And according to that, we need to provide a area of steel equal to 337.95 mm square in the compression region. Okay, so for the current problem, based on this, I am providing for the tension zone, I am providing 5 bars of 20 millimeter diameter, and for the compression region, I am providing 3 bars of 12 diameter. Okay, so please take a note of this result. So for the tension zone, I'm providing 5 bars of 20 diameter, and compression region 3 bars of 12 diameter. Okay, so AST minimum in the compression region is 338 millimeters square. Okay, so option E is the correct response. Okay, please make sure that you check uh, the values that we recently got, and if there is any problem, we can always discuss in the next class.
Yeah, okay, sir. Sure, sure, sir.
Okay. So yeah, I will proceed to the final problem now. So option E is the correct answer. And finally, once we have designed for the uh, flexure, we need to design for shear. Okay. So I'm going to make a sketch now. Okay, we'll come back to this later. Also, please bear with me. I will take up to 8:15. So it is having a width of 300 millimeter and overall depth is 600 millimeter. Okay, now I'm going to provide the longitudinal reinforcement. So we are going to provide 5 bars of 20 mm diameter and 3 bars of 12 mm diameter. Okay, this is going to be useful for us while designing the shear reinforcement. Okay, okay, we need to provide 135-degree hooks. So that is 5 bars of 20 mm diameter and this is 3 bars of 12 mm diameter. Okay. 5 by 4 of 20 square multiplied by 5 and here we have pi by 4 of 12 square multiplied by 3. Okay, this is going to be useful for us while designing the shear reinforcement. Okay, AST provided is 1570, 1570.8 mm square. This is pi by 4 into 12 square into 3. Yeah, that is 339, 339.3. Okay, so now let us proceed to design the shear reinforcement. Okay, so we have again for the n number of time we have already discussed it so much already, but still we'll proceed now. VUC plus VUS. Okay, and VUC is equal to tau C into BD. Okay, and here uh, tau C depends on PT and FCK, right? By now, I think it will be by heart. Clear, this concept would have been so clear since we have solved so many problems. And here PT is the area of steel in the tension region, that is 100 AS by BD. Okay, 100 into 1570.8 divided by 300 divided by 550, right? So PT is how much?
0.952.
Okay, thank you for the response. Yeah, 0.95 is the correct answer. 0.95%. And we need to have a look at grade of the grade of concrete is M30, if I'm not mistaken. Yeah, M30. M30. So using these two, we get the value of tau C as how much? 95.95. So we get a value of between 0.59 and 0.66. I'm getting value of 0.65. Okay, tau C is point, or to be precise, I'm getting a value of 0.647 MPa. Okay, now let us calculate the value of uh, VUC is equal to tau C BT, that is 0.6 yeah 0.647 into 300 into 550. So VUC is how much? 10.
6.7.
Yes, thank you. 106.7 kilonewton. But we forgot to determine the equivalent shear. That is VUE is equal to VU plus 1.6. Yeah, 1.6 TU by D, right? 1.6 TU by D, right? So we have already found out that the equivalent force is 426, uh, corresponding to a torque of 80 kilonewton meter. For that, we need to add a value of 60 kilonewton. Okay, 60 plus 426.6. 60 plus 426.6. I hope that this is clear, this step, right? Sir, I hope you got this concept why we are doing this, right?
Yeah, got it.
Yeah. Okay. Now VUS is equal to VUE minus VUC. Okay, now it is very much straightforward. Yeah, sorry, it has to be VUC. It is VUE minus VUC. For that, okay, let us proceed very quickly now. That is 486.6 minus 106.7, right? So VUS is equal to how much? 380 kilonewton. I'm getting a value of 380. Now, yeah, VUS is equal to 0.87 F by ASV into D divided by SV. Now, what is the value of ASV? We are considering 12 stirrups because again the value of shear is very high. Pi by 4 into 12 square multiplied by 2 gives us a value of 226.2 mm square. 0.2 mm square. Okay. Now let us substitute this value over here and find out the value of SV, that is 0.87 into 415 into 226.2 into D is 550 divided by 380 into 10 to the power 3, and solving we get the value of SV as
118.
1,
118.14.
okay, 118 is it? Okay. So yes, 118.2 mm square, sorry, millimeter. The answer is absolutely right. Yeah, so option B is the correct response. Okay, so yes, so I think we can go ahead and complete this drawing now. Okay, so we can say that we can provide two leg 12 dia stirrups at 110 mm center to center. Okay, so yeah, this is the correct final answer. So I think with that, we have come to the end of today's session. So, thank you for joining. And if there is any questions from today's lecture, or any other doubts, please feel free to contact us through the discussion portal. Next week, we are going to take up the design of columns. Okay, I think weeks 9 and
Okay.
10. In weeks 9 and 10, we'll be doing columns. Then week 11 will be serviceability. Then design for pond. And then week 12 will be the design for slabs. Okay. Thank you
Okay,
so
sir.
much.
Okay.
Yeah, thank you so much for
Thank you very
joining.
much, sir. Very clearly, you are explaining one by one. We understand very all is good, sir.
Okay, okay. Thank you so much for the kind words. And yeah, we'll continue throughout the rest of the journey, and we'll try to maximize the learning outcomes.
Sure, sir. Thank you very much.
Okay. Good night. Meet you again next week.
Yeah, okay. Good night, sir.